Welcome back to the lectures in chemistry and on the topic of atomic structure and chemical bonding. My name is Mangala Sundar. I am from the Department of Chemistry, Indian Institute of Technology, Madras. I would like to discuss a little bit on the approximation methods. But this lecture I would like to introduce what is called the perturbation theory. There are three possible cases that we have to consider. One is called non-degenerate state perturbation theory. PT. There is a slight variation of this is the degenerate state perturbation theory, and these are both time independent Schrodinger equation solutions. And in molecular spectroscopy, where we have some basic relations that can be obtained from solving quantum mechanical problems, we need to study what are known as first order time dependent perturbation theory. Okay, perturb means disturb very slightly. Okay. Otherwise, it's not perturbation. It's a disturbance and all kinds of things. What we mean by that is, in order to understand the basic philosophy of perturbation theory, one must also go back and recall that in quantum mechanics only a few problems that can be solved exactly. You recall from your earlier quantum chemistry that you have done the particle in the one dimensional box, the particle in probably n dimensional box with infinite potentials, boundaries, and with no potentials in between in the region, and perhaps with some potentials in the region, and you study slightly more complicated problems. But the moment you put the potential energy, it's not possible to solve this for arbitrary potential energies exactly. Okay. Therefore, potential free particle in a box problem is an exactly solvable problem, one dimension, two dimensions. The particle on a one dimensional, that is a single ring, or on the surface of a sphere, for example, these are solutions that can be solved exactly using mathematical methods. And the harmonic oscillator, a simple harmonic oscillator, can be studied by analytic methods in quantum mechanics. And the last, of course, that you have seen is the hydrogen atom, in which the atomic orbitals are obtained in precise mathematical forms by solving the three-dimensional Schrodinger equation in a spherical coordinate system using r, theta and phi. So these are the problems for which exact solutions are available. Now, if you place the hydrogen atom in a magnetic field or in an electric field, and you want to study how these energy levels of the hydrogen atoms are changed or disturbed or different in the presence of the field, then one has to use the premises of the exact solution, that is the field free solution, and then build corrections to the field present cases. And that is possible in certain cases, namely when the fields applied are very small and they do not disturb the energy levels by a large amount, and also the fields are such that they do not change the entire basic structure of the quantum system. So exactly solvable models in quantum are few, and perturbation theory builds on adding corrections to analytically solvable models, exactly mean analytically solvable models using a systematic procedure. In order to do the mathematics semi formally accurately, okay, it is not possible for me to do the mathematics very precisely using the theorems and so on, the theory of perturbation operators and so on, leave all those things out. Somewhat semi formally, in order to do this, we introduce a parameter called perturbation parameter. Okay. Typically what is meant by a perturbation parameter? Let us take the hydrogen atom case. The hydrogen atom, if you recall, the ground state has n equal to 1, L equal to 0 and m is 0. These are the angular momentum quantum numbers, both of which are 0, and that is a 1s orbital. The energy is given as minus 13.6 eV. You know that from your textbook quantum solutions. The next one, when you go to n equal to 2, there are 4 energy states, the 2s and the 3 2p orbitals, all of which have the energy minus 13.6 by 4 eV. Okay. What about the next one, n equal to 3? There are 9 solutions, all of which are identical, namely 3s, 3 3p and 5 3d solutions. They all have the same total energy, and that is given by minus 13.6 by n square, where n is 3, therefore it is 9 eV. Okay. Now when you say we put the hydrogen atom in an external magnetic field or in an electric field and say that it perturbs the states of the hydrogen atom, it does something to disturb the energy levels of this, the degenerate energy levels, and does something to that. The order of magnitude of correction, that is the perturbation, has to be roughly, if you take any 2 levels which are to be studied through some transitions and so on, the order of magnitude that you can think of is the difference between the 2 energy levels that you have. Here it is minus 13.6 and minus 13.6 by 4. The difference between the 2 is minus 13.6 by 3 by 4 times 13.6. The perturbation has to be at least 10 times smaller than this difference between the 2 energies in order for this to be treated by the methods that I am going to describe. Okay. So if you are thinking of many energy levels in a quantum system, and if you want to study simultaneously the transitions that take place due to external influence, which cannot be solved analytically, you can use perturbation theory, provided the magnitude of the perturbation divided by the pair of energy levels that this perturbation may actually disturb. Suppose you have 2 energy levels, E1 and E2, in this case 1s and 2p, 2s or 2p. Okay. This difference, which is given by minus 3 by 4 times 13.6 eV, okay, the perturbation magnitude which you call by some quantity, say the magnitude of perturbation as V1, okay. The magnitude can be treated as perturbing provided V1 by E1 minus E2 is much less than 1, is of the order of 10 or more. Okay. Here magnitude E1 minus E2. This is a rough guide to tell you that perturbation theory works very well if this ratio is about 10. If this ratio is smaller than that, it is even better. but if the ratio is larger, say about 5 or 4, you have to watch. The perturbation corrections that you calculate may not be sufficient, in that it may not be enough to calculate 3 terms or 4 terms, maybe you need much more. But if the correction term is of the order of magnitude same as the energy difference, you have a serious problem. Perturbation theory is not very useful for such cases. Okay, there are other methods for dealing with them. So when you define what is meant by a small magnitude, or when you say what is perturbation, this is what is to be kept in mind, that if multiple energy levels of a quantum system are studied and the disturbance between these energy levels due to an external influence, how these energy levels change due to that, then the magnitude of the perturbation divided by the corresponding differences cannot be cannot be less than about 8 to 10. This is a rough guide for you, and there can be maybe 1 or 2 problems. I will have that in the lecture notes when I give the assignments, so please refer to my website for some problems related to that. Okay. Now in the remaining time of 5 minutes, I will just summarize some of the solutions that we have to recall in order to study perturbation theory formally. So I will just summarize the solutions of the particle in a one-dimensional box. Box, which is, if you recall, V is infinity outside the boxes and V is 0 inside the box. So the boundary region is inside the box, the boundary region is the infinite potential region, and you remember that the solutions psi n, n goes from 1 to infinity, of the particle coordinate, if you call it x, the one degree of freedom coordinate inside the particle, inside the box, that is given by √2 by L, where L is the length of the box, sine n pi x by L, L length of the box, and the energies En are given by h square n square by 8 m L square. Okay. N is equal to 1, 2, 3 to infinity, all the energy levels of the particle in the one-dimensional box. And likewise for a particle in a 2D box. So let us take a square box, that is x is from 0 to L and y is also from 0 to L. That is the box that you talk about, a planar region which is a square region. Then the wave functions are now given by two quantum numbers psi n1 and n2, and because it is planar, the 2 orthogonal coordinates in the plane we can write as x and y, and in terms of x and y you remember that the wave function solution is 2 by L sine n1 pi x by L sine n2 pi y by L, and the energy, which is also a function of the 2 quantum numbers now E n1 and n2, is given by h square by 8 m L square within brackets n1 square plus n2 square. You remember these solutions. And likewise the solutions for a simple harmonic oscillator model may be recalled. The wave functions are given by a normalization constant, which itself is a function of the quantum number n and is given by an exponential factor, which I will write using a constant alpha x square by 2. Psi n is a function of the harmonic oscillator coordinate x, and then it is also multiplied by the Hermite polynomial root alpha x. What is the alpha? To get the notation correct, let us write these things carefully. Let me see, I think I should be able to do that. The Hamiltonian for the harmonic oscillator is minus h bar square by 2m d square by dx square, which is the kinetic energy of the harmonic oscillator, plus half k x square, where k is the force constant. Okay. So if I recall the constant alpha, I think it is given by the constants in the Hamiltonian, I mean the physical system that we talk about, it's in terms of Km by the Planck's constant squared. I believe it should be square root. Okay. Or if we have doubts, we can check, because you see alpha, root alpha x is to be dimensionless. That is alpha x square that you see here is also dimensionless. So alpha has to have the dimension of 1 by L square. X is the length displacement from the equilibrium, so alpha has to have the dimension of dimensionally not 1 by, alpha is not equal to 1 by L square, sorry, alpha must have the dimension of 1 by L square, L to the minus 2. So you can check that the force constant, you see force constant is the mass T to the minus 2, force constant times the x square gives you the energy, so ml square T to the minus 2 is energy, and if you multiply by mass, and h bar is ml square T to the minus 1 this whole square. So if you calculate this, you see you are getting square root of this, comes out to alpha as 1 by L square, because the m's cancel out with the m square, and the T to the minus 2 cancel out with the T to the minus 2, and the L square becomes L raised to 4, half of that is 1 by L square. So sometimes you should do these things by looking at the dimensions, and it's very easy afterwards not to forget these things. So the alpha is the parameter with which you define the harmonic oscillator wave function, and alpha contains the physical information, that is the mass of the particle and the force constant of the particle undergoing the simple harmonic motion. That's all the information that you need, and everything else is given in terms of the physical content, namely the wave functions, the energies, and so on. So what is the energy for the harmonic oscillator? ENs are given by h nu into V plus a half, where the quantum number V is 0, 1, 2, 3, etc. And what is nu? Nu is a frequency factor, and again this frequency is given in terms of 1 by 2 pi square root of k by m, again the physical constants of the problem that you talk about. So if the system has a higher force constant and a smaller mass, its harmonic frequency is much higher. If it has a larger k, a smaller k and a larger m, it has a lower frequency, and so on. But this is the harmonic oscillator solution. This is an exact solution, okay? And you can often also write this as h bar omega times v plus a half in terms of the angular velocity omega, which is obviously 2 pi times nu, because there is no trick here. H bar omega is basically h by 2 pi times 2 pi nu, and see it is nothing other than what you have written down, h nu into a v plus a half. Okay, so angular frequencies are like that. So this is the harmonic oscillator solution, which you have to remember when we talk about perturbation theory. And likewise, in the next lecture, I'll also discuss the hydrogen atom solution when we need to know. That is, we need to know solutions of what are known as model problems, which are perturbation free. And then when we put in the perturbation, how do we solve the system systematically, term by term, using an infinite series, is what I will do in the next lecture. So perturbation theory will be in the form of a series solution for I mean thankfully we will not do infinite series, we will only do a series solution with 1 or 2 terms. The first term is called the first order perturbation theory, the second term is known under the second order perturbation theory and so on. Until then, thank you very much.